is called The Flipped Classroom. Okay, guys, I'm gonna go over a few things. We're gonna do things a little different for this lecture, and probably for a few lectures moving forward. There's a lot of different ways to present material in college algebra or any class. Especially what's neat with these lecture formats that we can do now, we can play around with some different delivery styles. And today I've decided to do that because I've already made a really great lecture for section 2.5. I made it earlier this semester for my other class, and I am very proud of it. So I thought, well, why in the world would I make another lecture if I've done one already? And so what I'm actually going to do today is called a flipped classroom. So I'm going to take questions from 2.3 and 2.4 today. So I'm going to write that down. 2.3, 2.4 today. And then I'm putting the lecture for 2.5, the actual lecture. This one's going to be called 2.5A, just what we're talking about in class today. But the actual lecture, 2.5, will be in your YouTube, in your lecture videos once I get there. Here, I can do that right now. So that way when you're watching this, you'll already see it. I just want to make sure it's in there so you can watch it. And you can watch this. This one won't take long. So we're not going to be long today at all, unless we have a ton of questions from the audience over yesterday's lecture material. Here we go. Yeah. So let me put this. Hold on. Give me 1 second, guys. I won't get rocking in the one. So business. You guys are the college algebra. Yeah. 7-week. Boom. Okay. So you can watch the actual lecture video whenever you want to watch it before Monday. And what's going to happen on Monday is when we come in on Monday, I'm going to ask you if you have any questions about that video. And I give you the homework in it, right? So if you have any questions about the video, about the homework, anything like that, that's what we're going to cover on Monday. Now, if you watch these outside of class, which a lot of us do, and that's fine. If you want to send me a question, that's fine as well. Okay, I'll cover that question in the Monday lecture when we get back. So this is called the flipped classroom. And really what that means is you kind of go learn the material. For us, it's just going to be watching the lecture. You go learn the material outside of the classroom, and when you come back, we talk about it. Okay, so the discussion happens afterwards, which really makes sense, right? You go learn something, and then you come back and you go, oh, this made sense. This didn't make sense. Let's see what all works and what doesn't work for us. Okay, and I won't do this for every lecture. And when I do, of course, you'll know from me posting it in there. But I know that this 2.5 lecture was really good at the beginning of the semester, and I know that's goofy. That might sound goofy, but if you make a good lecture, I mean, why ruin it? And it's nice now; it's on video. Like I can show it to you. It'll probably be better than what I can deliver this morning. Okay, so I did want to go over a few people sent me questions about 2.3 and 2.4 that watch the stuff online, and it had to do with 2.4 mainly. So I'm going to start there, and if you open your book up, this is on page 267, and it had to do with the parallel and perpendicular line and the average rate of change. So 2.6, it was number 21, I believe. Yeah. 21 says, write an equation in slope-intercept form of a linear function f whose graph satisfies the condition. So 21 says the graph passes through, where am I? Negative 6, 4. And it's perpendicular to the line that has x-intercepts of 2 and a y-intercept of negative 4. And this is a tricky question, right? We've got a perpendicular line. Jake, can you get that door for me? I know Mr. Thomas doesn't want to hear the math lecture. I know we've got a perpendicular line. So I know that remember the slopes of perpendicular lines are going to be opposite reciprocals. Now this line though goes through these two coordinates. So what it's giving us two coordinates here for our perpendicular line. I'm going to write those two coordinates out. Remember, x-intercept of 2, that means 2, 0. Y-intercept of -4 means 0, -4, okay? So we know the line, look, I'm going to get real visual with this, but if I wanted to graph our perpendicular line, I didn't really get that visual in the lecture yesterday. 2, -4, so I don't know what our line's going to look like, but 2 and then -4. 1, 2, 3, 4. So this is the line we're perpendicular to, right? And we're trying to find some other line. Now it goes through -6, 4. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4. Right here. And so I can kind of see that this line, if it's perpendicular to this one, it's going to cut through right here somewhere, right? I mean, it's going to go like this. It's going to hit a perpendicular, but we need to find the equation for it. Well, if we're going to find the equation for this line, we need to find the slope first. So the slope for the other line, though, we're going to do a change in y, so -4 minus 0 over 0 minus 2. So -4 over -2. So we get a +2 for this slope, right? And this looks like a +2 slope, like you go up 2 over 1, up 2 over 1. Yeah, you got a nice +2 slope. Well, that means our perpendicular slope, which is what we're looking for, would be, remember, you flip it and change the sign, right? -1/2. So now look, we've got our slope. We've got our coordinate that we go through. So now we just need to use the point slope form. So y minus 4 equals -1/2 times x. Now it's +6, right? Because it's minus and -6. And then we're just going to solve for y. So distribute the 1/2. Y minus 4 equals -1/2 x minus 3. 1/2 times 6 is 3, right? Negative because it's negative times a positive. Add the 4. And we get y equals -1/2 x plus 1. Now, I think they want to write it as a function. They want you to write this as a function. It says form of linear. Yeah. So in the example, it says write an equation in a slope-intercept form of a linear function. So we're just going to write this as f of x equals -1/2 x plus 1. And now if I want to graph this one, I'll use a different color. It's not going to be too different. I don't know if it'll pick up well on the page. But if I start here, I'd go down 1 and then over 2. Yeah, you can see that this line will go right there. And look, see how it hits at a pretty perpendicular angle, right? We've got the purple line, which has the x-intercept of 2, y-intercept of -4. We found its slope. So that means if we're looking for a perpendicular line, remember, if it's parallel, it'd be the same. But if we're looking for a perpendicular line, we just have to flip it and change the sign. And then we knew our line went through -6, 4. The question gave us that. So we've got a coordinate and a slope. And then we just did what we've been doing really all through 2.3 and 2.4, right? And then we found our equation. Now, it didn't ask us to graph it. I just wanted to bring in the visual of graphing because I know I didn't do that really in the last lecture. Okay. You remember this, Janie, from last semester? Yeah. Yeah, if you guys came from Developmental 2, the Developmental 2 class in the first 7 week, we saw this a lot, right? It was we had a whole section on it, actually. So it's kind of nice whenever you guys come from that class that you've seen it. Now, if you haven't had a math class in a while, it's a little different. And I teach it like you haven't seen it in a while. Okay, let's do the average rate of change. That was the other question. And I'm going to steal an even one. This is number 18 on that same page, page 267. It says find the average rate of change of the function from x1 to x2. So we've got f of x equals the square root of x from x1 equals 9 and x2 equals 16. Now, this is not a intermediate algebra problem or developmental 2 problem. So now this one, though, remember, we're not going to have straight lines here because it's a square root. It's not a straight line. But what we're trying to find is the secant line between 9 and 16. So I'm not going to do a visual representation of this. I did that in the lecture. If you go back and look at the lecture, I drew this out and I kind of drew the secant line. So if you want to go look at that, that's fine. But what I am going to do is find the y values for each of these coordinates, okay? I've got the x values. I need to find the y values. So the y value for f of 9 would be the square root of 9, so it would be 3. So really the coordinate here is 9, 3, right? Remember that was the nice part about using the function notation. Here's the x value and it pops out the y value. 16, square root of 16 is just 4, right? So we wind up with 16, 4. Okay. Now to find the average rate of change, we just use these two coordinates for our slope. So average rate of change, the change in the y, so I'm going to do 4 minus 3 over 16 minus 9. So you get 1 7. Is that right? 4 minus 3 is 1. 16 minus 9, 7, yeah. So you get 1 7. That's the average rate of change. Okay. So you just, this is, if you go back and watch the lecture from yesterday, I probably made this a little more complicated than it had to be. Yeah, it is what it is. Okay. But this is all you really have to do. You plug in the x to get back the y, and same thing down here, plug in the x to get back to y. The question has to give you the x values. And I'll tell you on the test, I'm probably going to give you one of the real world examples we did. I can't remember. I think we looked at, did we look at a stock Apple or something? No, TJ Maxx. That's what it was, because my wife shops there too much. Okay. Yeah, if you look at, you'll probably have like a real world example like the TJ Maxx example. And then you'll also have a equational example like this. And if you do plan on going on to a business cal, a lot of us are in like the ASB degree and you have to go to business cal. This is going to be something that pops up more. And that's why it needs to be talked about. It is a college algebra concept. It's just that it really does lead you into the business cal questions. Okay. Great. Okay. I wanted to go over one more example, and it's one of my favorite examples in the entire book, actually. Hands down, one of my favorite examples. I'll even like zoom in on this thing, old school zoom in style. If you don't have the book in front of you, that's fine. We're going to talk about this example a minute, and you can see I've drawn on it before because I just love this example. I love this example. I'll tell you, my background actually is in statistics. That's what my master's is in. So this is kind of a stat example, but it's not. I mean, it's in all intents and purposes, it's a college algebra example. This is number 92. Let's look right there. Number 92 in your book. It's on page 257. And this graph talks about happiness and the percentage of people that call themselves happy. That's the Y. Percentage of people that call themselves happy, and the annual per capita income for countries. That's the X. Now let's read up here. It says, just as money doesn't buy happiness for individuals, the two don't necessarily go together for countries either. However, the scatter plot does show a relationship between a country's annual per capita income and the percentage of people in that country who call themselves happy. So I guess they just went around and they surveyed citizens of different countries, and they asked you, do you consider yourself happy? And what happens, the percent that said yes is given here. So like if we looked at, let's say Mexico right there. It's kind of hard to see right there. Boom, Mexico, right? You guys see that? Mexico, almost 90% of citizens in Mexico consider themselves happy. Yet the per capita income is around, I'm going to say like 8,000 per capita income in dollars, okay? But then on the flip side of that, I mean, about the same annual income, you got like Russia down here, 40% consider themselves happy, and they have about the same annual per capita income, right? So it doesn't really sound like there's a correlation here between like lower income and happiness, right? I mean, to me, it kind of seems like with some of these, it's like temperature, right? You looked at average temperature of Russia, Moldova, not Zimbabwe, but not Tanzania. So maybe there's not that correlation, but Ukraine. I mean, there's something else going on here, right? But that's not really what this is asking us. And I'll tell you, that's another issue with stats. You can't just make assumptions and say, oh, that must be it. Okay. Let's see what the questions ask. I like how the answers will vary. Draw a line that fits the data so that the spread of the data points around the line is as small as possible. Use the coordinates of 2 points along your line to write the slope-intercept form of its equation. Express the equation in function notation and use the linear function to make a prediction about national happiness based on per capita income. So yeah, and you can see I've already kind of drawn a line there, but the goal of a predictor line, okay, the goal of a predictor line is to cut all the coordinates in half, where you have 50, like it's almost like a fence line. Actually, it's a perfect way to think of it, is a fence line, where half of the coordinates are on one side of the line and the other half of the coordinates are on the other. I don't have a pencil in front of me, or I could kind of show you. A lot of times when I give this example, students want to make the line down here, right? Kind of like if you connected Russia and US. But if you connect Russia and US, you can see like 100% of the coordinates are above it. You want to split it, kind of like if you had siblings as a child and one of you had to cut the pizza and the other one chose which pizza they got. I don't know if you had to play that game, but whoever's cutting that pizza is making sure it's perfectly in half. Okay. So look, we can choose any coordinates we want to split this. And I'm going to choose, we don't have to go with US. Let's go with Norway there. I'm going to choose Norway, and then I'm going to choose like Jordan. If I drew a line from Norway to Jordan, you can see it kind of splits the coordinates in half. So Norway, the happiness is about, let's say 91. Okay. Now look, that's our Y value. So I need the X value first. Okay. So the X value for Norway, we're going to do it in thousands of dollars. So we'll say, what do you think that is? About 27? Yeah, that sounds good. So 27, and then we'll say they've got a 91% happy. So guys, on paper, that's my coordinate for Norway, 2791. So then let's choose another. So what did I say, Jordan? Jordan looks like they're about 4,000. So we're going to use 4. And then they are about 60, I'll say 62% happy. So boom, I've got my 2 coordinates. Now this just turns into a regular finding the equation of a line example. And it's in 2.3. I mean, this was before the parallel, perpendicular, all that stuff. So it's just a regular finding the equation of the line example. I'm gonna back out up here and then move the book. And I'm just gonna solve this one out like it's a regular finding the equation of a line example, okay? You guys tilted. So we've got to find the slope first, right? 62 minus 91 over 4 minus 27. I don't have enough fingers and toes for that one. So 62 minus 91, negative 29 over 4 minus 27. I could have done that one. That's negative 23. Divide those, and we're going to get a long decimal. And you know what? Because it's a real world example, I'm going to round it to decimals, okay? I'm going to round it to 2 decimals, 1.26. But we're going to sit here a minute and talk about what this 1.26 means. And that's really why I wanted to talk about this example, okay? What does the slope mean? We'll interpret the equation here in a minute and make predictions. But what does the slope mean? Now, remember, back from the lecture before, the slope is the change in y over the change in x, right? Now, for us, let's think of what y is. The y was that left-hand side of the graph. That was the happiness, okay, percent happiness. We'll just say happy. And then x was income, per capita income. So for our example, 1.26, I'm going to write that as a fraction, okay? 1.26 over 1. And we're going to talk about what that actually means, what we've found about our trend line. Now, we know this is the trend line. It's not perfect. And we can tell that there's a lot of coordinates that don't line up on this trend line at all. But we've got to remember, the slope is all about change. It's not about, the actual coordinate. It's about the change in the coordinates. And what this is telling us is that, look, remember, this was in thousands too, guys. That one is really 1,000 because I wrote these in thousands, okay? Better there. For every increase of $1,000 in per capita income. That's the X. For every increase of $1,000 in per capita income, that is delta X, okay? We can expect an average increase, of 1.26% of citizens to call themselves happy. I know that's a long write-up. I'm not expecting you to do this, right? I mean, it's multiple choice. Okay, so for every increase of $1,000 in per capita income, we can expect an average increase of 1.6% of citizens to call themselves happy. Okay, that's what our slope is telling us. It's telling us about the change and the relationship of the change between citizens' happiness and per capita income. Kind of neat. Okay, kind of cool. Okay, now let's finish this out to find the actual equation. I need some more paper, right? Come on now. So we found the slope, it was 1.26. Remember, you can use either coordinate here. So I'm going to use the second one just because it has a smaller number. So we know our slope is 1.26 and the coordinate is 462. So y minus 62 equals 1.26 times x minus 4, right? Distribute the 1.26. So we get y minus 62 equals 1.26 minus 4 times 1.62 or 26 is 5.40 or 5.04. There's an X there, right? And then I've got to add the 62. And I get y equals 1.26x plus, now 62 minus 5.04, 56.96. Oh, they wanted us to write as an equation. Let's say, now remember the y value is happiness, right? So this is a predictor of happiness. So I'm going to use capital H. 1.26x plus 56.96. That makes more sense, actually. And this is kind of like, this is a straight trend line. Like there's no, I mean, we saw it's not that the coordinates were that close to this trend line, but we can make predictions off of this. So let's say I went online and I found like annual per capita incomes of certain countries, right? And it turns out that Ireland's per capita income is, and actually it kind of says it here, about $23,000. Now, remember, for our equation, that's going to be 23 because we wrote it in thousands. So I'm going to pop this in and see what our line predicts Ireland's equation or Ireland's happiness percentage to be. So 1.26 times 23 plus 56.96. So it predicts it to be 85.94. So pretty happy people, right? Now, I'm going to go to the book now. And we're going to zoom in again. We're going to find Ireland on here and see if that was high or low. You can see Ireland is right there, right? And Ireland, actually, the people in Ireland replied that they're pretty dang happy. I mean, 95%. It's almost the low. I think the highest is the Netherlands, right? But Ireland, about 95%. So actually, our prediction down here, our prediction of 85.94 was low. And that makes sense. Look, our trend line would be below that, right? And that's fine. That's not the point. The point isn't to get every single one right. There's no way that can happen. Okay. But it kind of introduces the whole trend line aspect of straight lines, which is something that is interesting to me. And you know what else I kind of think of this whenever I think of like if I was going to make assumptions based, like, because it's definitely a triangle graph, right? it's like, look, if you have a low per capita income, if you're broke, I mean, you're gonna be happy or not happy. Like it doesn't really predict the being broke doesn't really predict if you're happy or not happy. But what it does say is the more that you make, I mean, the more happier you are, and probably your needs are met, right? That's probably what's happening. When you're in this pocket over here, when you're the average citizen in this pocket, their needs are met, right? They're not hungry. They have shelter. They have clothes. So because of that, typically you don't consider yourself unhappy, right? That's the only thing I can. That's a pure assumption I'm making based off this graph, but that's kind of what I think of it as. And you know, let's be honest, you've never seen an unhappy person on a jet ski, right? And that's kind of what makes me think of that too. Whenever people are like, "Oh, you know, money doesn't buy happiness," well, I mean, yeah, I'm sure it doesn't buy happiness, but I can do a lot of cool stuff with a few extra dollars in my wallet. Okay, that maybe wouldn't make me happy, but it would get my mind off being not happy. Okay. Okay, so let's go back again and talk about what we're doing now. So that was really just a follow up on 2.3 and 2.4. I should call it that. I might rename it in your YouTube. So today we really talked about 2.3, 2.4, and then I need you to watch the video titled Section 2.5, okay? And then when we get back on Monday, I'm going to answer any questions from that. Look, if there's no questions, I'm not going over it, okay? If you've got no questions, I'm going to go on to 2.6, and we'll keep moving forward. I forget what 2.6 is actually over, but we'll keep moving forward on 2.6 or whatever the next section is that we're supposed to cover, okay? Questions, Danny? Great. I will see you all on Monday. Make sure to watch that video before you come to class. And there's no real homework for today. The homework will be in that video. I put it in the video.